During this past year, we've had the privilege of watching SpaceX attempt to land the upper part of Starship using the belly flop maneuver. But talking about it with my friends, I've realized that almost no one really understands how crazy what they're trying to do is. Mainly because it's really hard to imagine just how truly massive Starship is. The upper part, which they were using for the landing tests, is about 50 meters tall and about 9 meters in diameter. I mean, that's roughly like a 15-story building falling back to Earth in a completely controlled way. But have you ever stopped to think that out of the whole size of those space launchers, only a tiny part is what we actually want to transport? The clearest and most extreme example is the Saturn V, which the Americans used to get to the moon. All of that is what was launched from Earth, and only this is what came back. The reason for the enormous size comes from all the fuel and oxidizer needed. That's the main difference with airplanes. For example, the F-18 carries the fuel inside. However, it uses the air from the atmosphere as an oxidizer, since air is made up, among other things, of oxygen. And it uses compressors to increase the air density, so there's more oxygen, then it's mixed with the fuel and combusted. However, space launchers go out into space, so they can't take advantage of the oxygen in the atmosphere for combustion. Rockets are so large because they must carry 2 full tanks, one for fuel and one for oxidizer. From now on in this video, to simplify things, I'll talk about fuel, but keep in mind that it means the sum of fuel and oxidizer. Space launchers typically have multiple stages. In other words, they have an initial launch rocket that lifts them a certain distance, and then it detaches and they continue with another rocket. So each stage must carry its corresponding fuel. And there are 2 main reasons why more than one stage is used. The first is because the thrust generated by a rocket is optimized for a specific altitude. This is determined by the exit area of its nozzles, but as atmospheric pressure changes, the exit area of the nozzle should change. Also, for the rocket to operate under optimal conditions, since this would be very expensive, what is done is that the second stage of the rocket is optimized to provide thrust in a vacuum. The second reason is that by using multiple stages and discarding one, the weight is drastically reduced. Therefore, for the same rocket thrust, the acceleration will be greater. Here we have a size comparison between the Saturn V, the launcher used by the Americans to reach the moon, and its Soviet counterpart, the N1. I'll make a dedicated video comparing these 2 rockets, but for now, which one do you think was more powerful? Well, it really depends on the definition of powerful that we use. If we take into account the payload they can put into orbit, for example, into low Earth orbit. As a reference, the Saturn could put up to 140 tons, while the N1 only 95. When comparing the thrust generated by these rockets at launch, the N1 generated about 45,000 kilonewtons, while the Saturn V generated 33,000 kilonewtons. I know how hard it is to understand how insane this is. Let me remind you that the engine of the F-18, operating at maximum, generates about 80 kilonewtons, which means you would need 410 F-18 engines to match the Saturn V and 560 to match the N1. The Saturn V can put about 45 tons more payload into orbit than the N1 despite generating 12,000 kilonewtons less thrust. How can this be? Well, it's because of the geographical situation that the Soviet Union had. The Baikonur station, from where they launched the rockets, couldn't take as much advantage of the Earth's rotation as the Americans did when launching from Cape Canaveral, much farther south. This is the reason why the European Space Agency carries out its launches from French Guiana, almost at the equator, and not from Europe. This is because every point on Earth makes a full rotation in one day. However, the closer you are to the equator, the greater the distance you travel in the course of a day. And since speed equals distance divided by time, the speed is higher. But how much higher? This is something I've always wondered about. Look at the difference in mass that the Saturn V can put into orbit compared to the N1. At the equator, it's easy to calculate Earth's rotational speed, given its radius and that it rotates once per day. Per day, you get about 1,667 kilometers per hour. In other words, a stationary person at the equator is moving at 1,667 kilometers per hour. At Cape Canaveral, with a latitude of approximately 28 degrees, the Earth's rotation speed is 1,471 kilometers per hour. However, in Baikonur, where the latitude is about 45 degrees, the rotation speed is 1,179 kilometers per hour. As you can see, a difference of about 20% in initial speed compared to Cape Canaveral. And in the aerospace sector, as you can see, this means a lot. It must be said that besides that, the Saturn V was more efficient in everything, practically. So it was much better at turning thrust into movement, and that's why it didn't need as much thrust. It's worth noting that the N1 never had a successful launch, which we'll discuss in a future video. If I see your support with likes. Regarding space launchers, mathematically what they do is provide the necessary increase in velocity to a payload, which will generally be a satellite so that it can stay in orbit. Since, as we explained a few weeks ago in the video about Earth orbits, to keep an object in orbit, it needs to have a fairly high speed. That's what the space launcher does. It gives it that speed, which in the aerospace sector is known as velocity increment, or colloquially delta V. That's why the Tsiolkovsky equation is used. This part here is the ratio between the initial mass and the mass of the rocket without fuel. You take the logarithm of that and multiply it by Earth's gravity at the surface. And be careful, because even if your rocket is on the moon, it's always used. The value of 9.8 is always the value of gravity at Earth's surface. And then this is multiplied by the specific impulse, a very interesting quantity always used in all orbital equations. In fact, force never appears, which took me some time to understand. For rocket enthusiasts, it's crucial to grasp this concept. Force is an instantaneous quantity, meaning a rocket generates a specific thrust force at any given moment in time. However, if the rocket applies that force over a period of time, as happens in reality, impulse comes into play. Impulse is defined as the product of force and time. But at the same time, it would also be interesting to know how much fuel is used to produce that force during that period of time. This is essentially specific impulse, which is where the confusion arises. If you search on Google, you'll notice that specific impulse has units of seconds. This is because after the Second World War, which is when rockets began to be studied in depth in the United States and the Soviet Union, they took the best German scientists. And in exchange for helping them develop new projects, they would be forgiven for having been part of the Nazi side. But the curious thing is that the Germans used the metric system, while the Americans used the imperial system. And to avoid confusion, it was agreed to divide the specific impulse by the acceleration of gravity in whichever units were being used. Gravity is 9.81 in the metric system and 32.2 in the imperial system. This way, no matter which system you use, the result for specific impulse will always be the same, since seconds are the same in both systems. For this reason, even if we study a rocket that's intended for deep space, the value of gravity at the surface of the Earth will be used, because it's a convention to ultimately obtain seconds. But another way to understand specific impulse is that for 1 kilogram of fuel, for how many seconds is your rocket able to generate a thrust of 9.81 newtons? So it really represents efficiency. The more seconds your rocket is able to generate that force with 1 kilogram of fuel, the more efficient it will be. This is the most intuitive explanation, but we wanted to explain the origin of specific impulse. Because surely, just like me, many of you wondered why the same value of gravity is always used no matter where your rocket is. Having understood specific impulse, we can now perfectly understand Tsiolkovsky's equation, which tells us that delta V depends on the logarithm of the masses, multiplied by the specific impulse and, if you notice, also by gravity. This value is included to cancel out the gravity that's being divided inside the specific impulse. With that information and equation, you can create a graph for a space launcher. It's a mess, but now it's understandable, where the y-axis is the delta V obtained and the x-axis is the amount of fuel it carries. The graph starts from 0, 0, since carrying no fuel results in 0 delta V. Your rocket won't take off. As the rocket's fuel increases, the delta V increases. If you notice, it seems that around this area there's a change in trend and suddenly it stops increasing. What this means is that no matter how much fuel we put into the rocket, the delta V wouldn't increase. And this is because there's a point where by adding more fuel, you increase the weight even more, and therefore you'll need even more fuel. To be able to carry that extra weight and to be able to carry that fuel, you're gonna have to add more and more and more. Something that makes a lot of sense and is pretty obvious, but it's striking to see it mathematically. The fascinating aspect arises when we repeat the process for a 2-stage rocket to ensure your comprehension of the procedure. We put a rocket with a certain fuel amount, calculate delta V, and repeat the process by adding more fuel. This generates infinite data points to plot a line. Well, when we do the same thing with 2 base stages, the rocket will weigh more. The second stage's structure, including fuel tanks and pump, increases weight. And that's why the delta V obtained for a single stage is greater at first. However, when we keep adding more fuel and it exceeds a certain value, suddenly the 2-stage graph intersects with the single stage one and the delta V obtained becomes greater. From this point on, mathematically, it's more efficient to use 2 stages. This is crucial in reality, where you must invest in design and manufacturing. Probably until you had to carry much more fuel, this idea of using 2 stages wouldn't be applied. Based on the analysis, rockets such as the Saturn V were designed with 3 stages, while the Soviet N1 had 5 zones. However, the Starship is designed to have only 2 stages. But there's a bit of a trick here, since for long-distance missions, the rocket would remain in a parking orbit around Earth and another Starship full of fuel would dock with it. All the fuel would be transferred to the initial Starship, and once this process is finished, the initial Starship would set off for the Moon or Mars. That's why the Tsiolkovsky equation didn't consider this process. In fact, in the same way, you can do an analysis to find out what the optimal fuel distribution is in a space launcher. To carry 100 kg of fuel in a 2-stage rocket, you could put 70 kg in the first stage and 30 kg in the second stage. Or 50 and 50, or 10 in the first stage and 90 in the second. Anyway, there are infinite combinations. Which one do you think is the best? Pause and put it in the comments, but do it so that when I give you the answer, you don't fool yourself by saying you already knew it. Solving Tsiolkovsky's equations for infinite cases yields a remarkable graph. The x-axis shows the percentage of fuel allocated to the first stage, with the remainder up to 100% going to the second stage. That is, if we use the data from the Falcon 9. This point would represent the case where 20% of the fuel goes to the first stage and 80% of the fuel goes to the second stage. And for this fuel distribution, you would get a delta V of 9.3 kilometers per second. If we now represent all the cases, you can see the optimal velocity increase. That is the fuel distribution that will give you the highest delta V. This distribution is approximately 87% fuel in the first stage and 13% in the second. These data are from the Falcon and are the results obtained using the Tsiolkovsky model. But if we now look for the actual percentage value that SpaceX uses in each stage, do you know where that point is? Exactly, it's practically at the maximum delta V. The reason it doesn't match 100% with the maximum obtained in the graph is because the Tsiolkovsky equation is super simple. It doesn't take into account the drag generated by the rocket or any other effects, but as you can see, it's amazingly accurate. Finding the optimal distribution for multi-stage rockets would follow the same process, albeit with increased complexity. But generally, all 2-stage rockets will always carry approximately 80% of the fuel in the first booster and the rest in the second. This is because what takes the most energy is leaving Earth. To put a satellite into orbit, you begin at a very slow speed, and you have to fight vertically against gravity to give the rocket speed. Taking into account that there's also air resistance, that's where the most fuel is going to be burned. This is because fighting against gravity in a direct thrust is extremely inefficient. Airplanes, for example, don't do that. They generate forward thrust, and it's the wings that create lift. That's why an A380, for instance, produces a thrust of around 350 kilonewtons. With its 4 engines, however, it can carry a weight of 6,300 kilonewtons, meaning that the lift is about 18 times greater than the thrust generated. And that's the key to airplanes. Going back to rockets, since SpaceX started broadcasting launches live a few years ago, I've seen it many times. A common question, what is max Q? As you can see in the little message that appears on the right, max Q is the point where the dynamic pressure is greatest on the structure. The definition of dynamic pressure shows that it depends on density and velocity squared. In aeronautical engineering, dynamic pressure is always represented by the letter Q, which is why it's called max Q. Well, when the rocket is launched, the velocity starts to increase, but as it ascends in altitude, the density decreases. Well, max Q is the point where the combination of these two is at its maximum. Below this point, density is high, but the rocket moves slowly. Above it, the vehicle moves very fast, but density is very low. Keep in mind that on the ground before launch, since speed is 0, dynamic pressure is also 0. The same applies when the vehicle is in space, where density and dynamic pressure are 0. From now on, whenever you see a space launch, you'll understand the math and physics behind it much better. Best regards. Remember to subscribe if you haven't already and check out the previous videos. This video features graphs generated by discretizing Tsiolkovsky's equations for many points using a brief MATLAB code.